Hello, can you hear me? Yeah. Awesome. Okay, cool. We go this way. Yeah, my name is Andrea. I work for Canonical in the current team. I'm not a scheduler expert. I'm not either a Rust expert. So therefore, let me tell you how to write a scheduler in Rust. Whoa. Okay, scheduling. First of all, very short introduction. You all know about scheduling way better than me. But I came up with this definition, try to be as compact as possible to define a scheduler. Often I have not often, but sometimes I have the chance to work with students. If any of you work with students, I strongly recommend to do that. It's very refreshing. It forces you to go back to the basics. And yeah, I came up with this, trying to be like as compact as possible. Basically, a scheduler needs to decide like where a task needs to run, when, and for how long. Yes. Like here. How about now? Okay, but yeah, so anything to say so far? Cool, I got it right. Perfect. I can show this to students. So why does scheduling matter? Usually we talk about scheduling purely in terms of performance, meaning that we want to provide a fair share of CPU. There's also the fact that we have been discussing for the whole morning about latency and throughput. They seem to be two different things. Like you either push something on latency and then you end up like making the throughput people unhappy, or the opposite. But it's not only that. We can provide like security capabilities through scheduling, for example, by isolating tasks to run on different separated cores to prevent hyper-threaded based attacks, for example. The scheduler can also help in terms of energy efficiency. We talked about that earlier. And of course, stability, like we don't want to have starvation, issues like that, keeping the system healthy, basically. So there's a lot of stuff here, and things can get complicated very, very quickly. So what's the situation in Linux right now? Well, Linux, as many other kernels, decided to go with the philosophy, with the policy of one scheduler to rule them all. We just have one scheduler. That's not entirely true because we have real time. But yeah, we have round robin, FIFO, deadline. Then there's the sched normal, idle. What else? Yeah, there's three real-time schedulers, basically. But the normal scheduling, like the old one, there's just one. We used to have CFS, 466. Now we have EVDF that improved certain things, didn't improve others. The development is still in progress. But the point is that it's really difficult to make everyone happy with just one scheduler. And it's really difficult right now to do experiments because like you usually need to do the same kernel workflows of recompiling everything, deploying in production, calling in production, an experimental analysis is risky and consequences are not very nice. It's also difficult to upstream changes, like the bar to access scheduling development is really high. I mean, unless you are a very experienced kernel developer with many, many years of like practice and knowledge. So it's really difficult to attract young people. I mentioned students earlier. It's like it's doable, but it's really difficult to convince and push students to do scheduling work because they get scared and discouraged, and they're scared to post the patches to the mailing list. So yeah, the point is the development is not easily accessible. So skex came in, there is this patch, there's a lot of discussion in the mailing list. The proposal is to have a pluggable way, a pluggable interface to like plug and plug custom schedulers implemented in eBPF as eBPF programs. This has the advantage of like the easy to experiment, ease of experimentation advantage. Like you can literally load a scheduler as if it was a user space program that would replace the default scheduler. And if there's a bug, I mean, there's a BPF verifier that guarantees that you don't have memory bugs. So your scheduler doesn't even load if you have something like that because there's a verifier. And there's also the fact that like this whole skex infrastructure has a watchdog where you can define like a certain time limit. And if your task isn't scheduled in that time limit, the skex subsystem will just kick out your custom scheduler and smoothly transition everything into the default Linux scheduler. So that makes experimentation much safer. It's also easy because it's very trivial. Like the skex has been designed to be like to not expose everything. So it exposes only certain, like you just need to implement a few callbacks in your eBPF program, and that's it. But the thing is like, so there's a limited programming model because in eBPF, you can't do everything. It's not Turing complete, even if you can do a lot and it keeps improving. But it's still limited by the programming model. And you have the usual kernel restrictions. Like we all know, like no use of floating point register, no use of like stack is limited, and other limitations. So that's why I proposed, why don't we jump to user space? We take a step further, and basically, yeah, we use the BPF layer to implement a bare minimal layer to bounce all the scheduling events into a user space program, and then use the user space program to implement the whole scheduler. In this way, what's the benefit? The benefit is that we can access to all the user space features, languages. I picked Rust because I just wanted to learn Rust, no particular reason. But potentially we can write, like, once you have the BPF layer, you can potentially write any kind of binding to C or even Python or Go, whatever. We can link the scheduler to any kind of user space library. Someone even said at some point that, yo, you can plug your user space scheduler into an AI model and let the AI decide the scheduling. Yeah, sure, you can do that. Probably, I wouldn't recommend to do that because maybe the AI workload would be much higher than the workload that you're trying to schedule. But yeah, you can do that. And you know, user space scheduling is not a concept completely new. I mean, there's Google that has provided this Ghost framework. It's basically, again, scheduling in user space. Initially, it was something like a completely custom solution based on queues of communication queues. Now, I don't know the status right now, but I know that they're planning to re-implement everything on top of skex. So, yeah, and one question could be why you didn't do the Ghost. You didn't reuse Ghost, mostly because I wanted to implement something right on top of skex. And yeah, the skex community is very welcoming and active. So that's why I did my thingy as a new experiment. So that's why I decided to try and write this project called Rustland. It's a fully functional Linux scheduler. You can use it. It seems to work more or less. It's written in Rust, but so that's something that I usually mention, like nothing to do with Rust for Linux, because usually the people are, oh yeah, that's Rust, therefore it's the Rust kernel part. No, it's just Rust in user space, regular Rust. The scheduler itself runs as a regular user space process. So there's a cool thing that like the BPF part needs to schedule the scheduler. So the scheduler needs also to schedule itself somehow. And BPF part is very minimal. It just bounces the task with a payload of extra information that are used that are provided to the scheduler. And then all the scheduling decisions are made in 100% in user space. And the thing is like, so the project is made of these two crates for those that are not experienced with Rust, are just libraries, let's say. There's a core that implements this layer from BPF to user space. And there's the scheduler itself. So what I like to highlight in this talk is more about this part, like the user space framework that allows people to implement schedulers easily and quickly, more than the scheduler itself. Scheduler itself, I mean, it works for certain workloads, but there's nothing special, more like a proof of concept. The thing is like that I want to highlight is this part and see if it's a viable option. Like, because initially when I started this only as an experimental project to show something to students. Like, so you guys can do, I don't know, you can write your own scheduler and you can test it. But I was very skeptical. Like, I was convinced like this will be unusable because the overhead of moving to user space will be so big. But yeah, anyway, yeah, this is how it works. Yeah, there are. I'm not going too much into details, but basically, the BPF part just intercept the skex callbacks. It stores the task into a single type of queue, just a single type of queue. There is not a type of queue, by the way. It's a ring buffer. The user space task consumes the task from the type of queue that is a ring buffer, and then user space. The Rustland core provides the APIs to so that the scheduler can assign a CPU to each task, a time slice, and then it sends everything back to the BPF component using another ring buffer. Specifically, like to consume from BPF, we use a BPF map type ring buffer, and to consume from user space, we use a BPF map type user ring buffer. Because we have like, yeah, in one way we need a different data structure, because one case the producer is the kernel, in the other case the producer is the user space. Initially, I was using BPF type map type queue that was relying on the BPF syscall. And the system has a consistent overhead, like, because every task, like every enqueue or dispatch event was actually calling a BPF syscall. That was a huge overhead. But even then, even in that case, it was still usable. So I was surprised. Once we moved to the like full ring buffers, we got like a really big improvement in terms of like way less overhead. Up to the point that now is pretty much like the overhead of the user space scheduler is like more or less like implementing the whole scheduler in BPF. So I'm really happy about this. Yeah, and thanks to like this part was done this part here was done by David Bernet from Meta and Jose Fernandez from Netflix. They both helped me to do this part. So big thanks to them. The scheduler itself, there's nothing special here. It's just a vRuntime based scheduler, similar to CFS, with the task priority, with task weight. There's just a small heuristic, very simple heuristic that tries to classify tasks in like interactive tasks and non-interactive tasks. And heuristic is just to look at the voluntary context switches, like it stores a moving average of the voluntary context switches, and if this average exceeds a certain threshold, it says like, okay, these tasks are interactive, so let me boost their priority. And there's also the fact that the vRuntime is already prioritizing latency. But this is like, it's pushing latency priority to the extreme, because like the workload that I wanted to focus on was the latency workload. And yeah, there's another thing, that time slice is adjusted based on the tasks that are waiting to, like the more tasks you have that are piling in, like if you try to overcommission your system, the scheduler will try to shrink the time slice. That makes everything bad in terms of throughput because you have more context switches, but it helps in terms of latency, at least according to the experiments result. There's also, okay, this is just, I want to mention this quickly. There's also low power mode, but this, I mentioned this just as a way to prove like how easy it is to do experiments with this, with Rustland, but that's skex in general. Like this was literally done in one day, because there was actually a bug at some point where I wasn't using the whole CPU capacity. So I would like even simply looking at top, I was seeing that even if I was over commissioning the system, the CPUs were not used at full capacity. And the consequence of that was that I was actually using less power. But I wasn't noticing any, I mean, the throughput was bad, but the latency was still good enough for like my typical usage. So I was like, oh, wait, let me reuse this bug as a feature. And because the problem was that I was allowing CPUs to enter idle state, even if I had like tasks queued waiting to be scheduled. And I was like, okay, that's a bug. But then I was like, well, at the same time, though, I can still have good responsiveness or fairly good responsiveness if I allow some CPUs to just go idle. And assuming that there are other CPUs active, because otherwise everyone will go idle, of course, and the system would just freeze. So that I changed the code to allow this, to add this simple logic. And I added this as an option because, of course, like if it was the default, everything would be super slow. But it actually seems to help in terms of power consumption. There's also a simple FIFO scheduler, just as a little proof of concept of using the Rustland core library. And the FIFO scheduler, it's like a fully functional FIFO scheduler, and it's less than 100 lines of code in Rust. So those things are really useful. Like if we need to show this to like a bunch of students, they can immediately understand what I'm talking about. And I don't have to dig into kernel details or BPF, what is BPF, what is skex. I can just show the scheduling policy and I can play with it. I think that's interesting. So yeah, that just quickly mentioning this. So the first one is something that I've been struggling for a long time. So the scheduler itself is a user space process. if the scheduler is a page fault, sometimes we need a kernel thread to be scheduled to resolve the page fault. But if the kernel thread cannot be scheduled because the user space task is like waiting for the page fault to be solved, what we have, deadlock. So yeah, that was tricky. Basically, the way that I decided to solve this is to pre-allocate a memory buffer in the scheduler, and I lock the memory. And then I had to change, I was like, now how do I convince Rust to perform allocations only from this area? Because that was the point. Like I can lock an entire and pre-allocate an entire memory, but then I don't know how to convince Rust to do all the allocations from there. And it's actually really easy. I didn't know, but you can define like a global allocator object, implement two methods like malloc and free, and then all the allocations done in Rust would be like bound into this global allocator object. So this is how I basically convinced the Rust environment to redirect all the allocations into this custom allocator. That is actually a simple buddy allocator, but that's fine because I don't need, like, the only things that I need to allocate in scheduler is just like custom task struct. And there's still a problem though, and I don't know if any of you have some good suggestion. So there is this compact unevictable allowed. If it's set to 1, the kcompact D would try to reclaim unevictable memory. So even if I lock the memory, I'm still getting like potential page faults because the kcompact D is just trying to unmap pages from there. So what I'm doing right now is just as soon as I start the scheduler, I set this to 0, like and I store the previous value when I stop scheduler. I don't know if there's a better solution, but yeah, if anyone has any idea. The other thing is that CPU plugging is not supported yet. So if you like if you have some CPUs offline and you start the scheduler, and then you put the CPUs online, the scheduler will continue to schedule on the previous set of CPUs. But it's something that I would like to add, but it's not very pressing because, again, the scheduler is pretty much a user space process. So I can just restart. I could potentially have a, I don't know, systemd script where I restart the scheduler when I when I add the alt plug, insert new CPUs. So is all of this really working? Okay, I had a demo, but I'm not going to show this because it's a PDF, where I posted the video where I was showing that I'm playing this game called Terraria while recompiling the kernel in the background. Yes.
I had a question about your previous slide. Is the hot plugging? So,
I thought, is it really working? Yeah, this one.
Is that something that should just be in sched.ext as opposed to having every user mode scheduler need to implement it?
Yeah, so sched.ext, yeah, is it possible to address this issue, let's say, at the sched.ext level? It's just that I'm not like, yeah, it's already done. It's not like a sched.ext thing. Like right now, I'm just checking. I'm determining the topology in user space, literally looking at what happens in FS. What I should do instead is to rely on some skedex capability that exposes me the right topology. And when something happens that changes the topology, yeah, I should adjust my scheduler to reflect what the topology change was. I'm not sure I don't think we have in skedex such event-based interface. It would be nice to have, absolutely. So yeah, maybe I changed my mind. Just changed my mind. Yeah, we should probably do something in skex to have like an event-based interface where like there's a topology change. I can intercept the event and adjust either my user space scheduler or the BPF scheduler accordingly. Absolutely.
One more question if no one has a question. So the ring buffers you mentioned, does that mean you have a limited size for how many tasks can run?
Yeah, it's not about how many tasks can run. It's more about is the scheduler fast enough at consuming these ring buffers? Yeah, right now it is, because like it's the BPF part that decides when the scheduler needs to run. So as soon as I have, so right now it works in this way, like if there's a task that wants to run, there's an enqueue called that is called. The enqueue would just store the task into the ring buffer. And that's one path. The other path is when a CPU goes idle, meaning that either a task expired its time slice or a task voluntarily releases the CPU, I just trigger the user space scheduler if there are queued tasks in the ring buffer. So it goes first, like it wins, the scheduler itself wins over any other task. So you basically, you never fill the entire ring buffer unless you have like a really intense burst of enqueue events. Let's say you have a fork, even if you have a fork bomb though, well, the fork bomb potentially can create an amount of task bigger than the size of the ring buffer. And in that case, like you fill the entire ring buffer before the scheduler runs. So if the fork bomb has a time slice, within its allowed time slice creates more tasks than the ring buffer, yes, you have this problem.
But so the ring buffer is only for communication, it's not the actual run queue.
Yeah, exactly. It's just for communication between the BPF part and the user space part.
Okay, thank you.
And if it's congested, what I'm doing, like if the ring buffer is full, I just dispatch directly. So it bypasses the scheduler. So it's not that you lose the task. Like it just goes straight, the system is entirely congested, but hey, you're under attack of a fork bomb. So that's the best I can do, maybe.
Okay, thank you. From a university perspective and students, this looks really cool to get them to use the changes they make as opposed to hypothetical systems. So thanks.
Yeah. Thank you.
I'm not sure if it's the right time, but I would probably debate this because in my experience at working at university, I mean, starting all these at university, it wasn't that particularly hard to get to. I mean, if you look at these pipe, or for example, implementation of the scheduler, if you have better understanding of C, I would say it's pretty simple to understand how it works and how to make modifications. I mean, and at the same time, there were, I only speak from a real-time scheduler perspective, but there were at least one big group using something similar, not implemented in eBDF, was a user space implemented scheduler, and they used that framework to implement all sorts of different schedulers to essentially back their theory when writing papers. It was working perfectly for them. I guess for me, when I started, it was essentially the same to understand how to implement something there versus how to implement something directly on Linux. And then at the same time, I don't think much of what they work on was then implemented anywhere really useful. So
yeah, no,
I'm fully convinced.
Just added on top of this. And there are many cases where people do these experimental schedulers. They show like on a paper that it is best, for example, then sched deadline, just to say. But at the end, when you try to bring that back to Linux, it just doesn't fit to the model, right? So at the end, there's a lot of wow, a lot of likes, blah, blah, blah. but the result back doesn't land because it end up not fitting on the kernel, right? And then it's somehow frustrating to keep seeing those things happening over and over again, and at the end not getting, okay, let's make the thing better.
Yeah, so I agree with you on the part that like it's not impossible, of course, to contribute to do some experiments right now. It's if you start from the FIFO, SCED FIFO, it's actually easy. I understand. The other thing is like how attractive is that? Like at least for my experience, if I say, okay, you have these two options. One, you can grab the SCED FIFO and implement your own theories or experiments, and then you compile the kernel, you reboot, you install that in a VM, whatever, and you do your test. On the other hand, I say, oh, look, you have the possibility to write your scheduler in Rust and just start the scheduler as if it was a user space program. So you can follow the usual change, build, run, the development cycle that you have with user space programs. If I bring these two things, these two pills to the students, they all pick the one where you say use Rust.
I would pick the kernel one, and then that's your experience.
I would pick the kernel as well because I did the same. But like I'm saying, statistically, like we
don't have a statistical okay, come on, we don't have
the last class that I saw, literally 99% were like super excited by the possibility to implement their own scheduler in Rust and having, because I don't know, maybe because it's Rust but I don't know exactly, but yeah. But I understand with Danielle. I mean, I was the same guy that decided to go on the kernel route. That is not the easy path; it's the hard path.
At the end, Mike. Okay, at the end, like this barrier of trying to do a small change on the kernel, it's the small part if you think on trying to develop a schedule, because developing schedule is way more complex than this barrier.
It's not just no, I agree on that, of course. But the point is like is more about democratizing scheduling development, meaning that it sounds bad maybe because we don't want like to accept a bunch of crazy ideas, but if more people are attracted to this, I mean, maybe a good idea comes from someone that is not special at all. I mean, we don't necessarily need people to be extremely expert on a field to collect some interesting ideas.
Sorry.
Oh yes, you.
Maybe it makes sense to split it up between undergrad and postgrad. So I see what you're saying with postgrad. From an undergrad perspective, there's a lot of value to have the students be able to just use their changes and gets them excited about kernel development in general. At least for my undergrad, we used some cooked system. We didn't use Linux. And so it would have been really cool to be able to do this. But I also think it can help development in the future in the sense that if someone puts some open source scheduler that's based on Linux, like every Linux version, they have to, bump it up and make sure it works on the latest. But if skex has a somewhat of a stable interface, it seems like.
Yeah, I would like to address the very profound comment by Daniel where he said, this is the easy part of making the contribution, like understanding where is the boilerplate and where to put this is the first week, and then there is the following, I don't know, 5 years, right? But I agree. But when in the conversation of bringing people to the kernel, we say, let's lower the bar, what do we say? Learning Git. Like, seriously? And we say email. What I'm trying to say is that there is initiatives in the Linux community to attract people to Linux, and and the bar get in things that I would say this is the easy part, because I know this stuff. Like there are things that when you learn them, you forget what it is to not know them. Like I don't, it's so you see what I mean? Like when Greg says I'm gonna make a kernel developer, he says fix a typo in the kernel. I'm not sure that's the difficult part, you know. So, but this is I don't know if I'm conveying what I'm trying to say. Like it's the easy part here, and also in other conversation, and I believe that they are both important.
I mean, I agree that it's a nice play toy and nothing else, seriously. No, the problem is, I mean, if I told the BPF people, the ShedX people several times by now, and if you look at how it's bolted into the kernel, it's an utter mess. And no, it's not going to that way, because either we clean it up completely and make the scheduler modular in general, or we just leave it out of tree. And it's not going to work that way. For a tool, fine. There have been pluggable scheduler frameworks in the academics world forever. There was one at Kansas University, then at Björn made one. Yeah, it's perfectly fine. Just keep it patchable into the kernel and be done with it. But explain to students that this is a toy, and if they really get the fun out of it and get the intention to contribute to scheduling, then they really should learn C and kernel programming.
It's an entry point.
Like, yeah, that's fine. That's fine. But then, don't inflict with that argument and really horrible thing into the kernel itself, because no, we are not playing toys.
A quick question. So, well, I kind of have similar skepticism about the helping on that early stage. One of the things that I've found very challenging is actually correctness and finding ways to test. And so I was curious what you were using to test the schedulers that people were developing, and how do we build kind of that sort of tooling so that that improves our...
Yeah, this is a generic topic. It doesn't involve just skex or user space scheduling. It's like, you know, usually what we do is benchmark, and it was like in the skex community, we use a lot of doing gaming benchmarks because it attracts people. Like the things that I've been focusing was latency again, because my whole point was literally to attract students at the beginning. Then, like I was going to show that I posted this video and it got quite viral, but got viral because, look, not because the schedule. So I love Foronix. And I'm very grateful of this article. It's like, it's not the scheduler showing promising results. Yes, it shows promising results. In that particular workload, my toy scheduler performs amazing because I can compile the kernel, play the video game at 60 FPS. Of course, it's not it's not a replacement for the default Linux scheduler. It's a replacement any kind of upstream scheduler. It's just a scheduler that works for that specific workload, and the benchmark was very focused on that specific workload. But the thing is that, like, you know, you have a way to. The point here was to prove, but 2 points actually. One was to prove that user space scheduling is possible, because like initially when I started the project, I was expecting to get 1 FPS, not even 20 FPS. And when I realized that I was getting like 60 FPS, and then I improved the things and I was getting 60 FPS even by compiling kernels or doing crazy things, I was, oh, that's cool. And the other point, again, is the ease of experimentation. Again, I can load this when I have a certain workload and stop this. If I have a bug, whatever, it just, you know, the skex watchdog would kick in and throw my scheduler off. So actually experimenting in production. And I have another slide that I want to show. So I received this message of a guy claiming, okay, read first and then I'll comment. So this guy is claiming, I pixelated his name because I didn't ask if I could show him. So that's the reason, but it's on the public Slack channel of skex. He's claiming that he's using Rustland and its render farm improved by 10–15%. That's amazing. I was surprised to see something like that. But, okay, I don't know if this was just pure excitement. I don't know if the measurement was completely off. But apart from that, I mean, I'm shocked to see that someone actually tried to use this in production. And somehow I mean, I was expecting comments like, dude, I tried your scheduler and it crashed my entire fleet or stuff like that. So it proved that it's usable. Again, like Thomas was saying, it's a toy and people can play with it.
Yeah, I would just like to add for the appeal to the students part. I used to be involved in developing the lab manuals and I was a teaching assistant. So I would actually spend the whole time with the students in the lab. And if you want to play with the scheduling policy and the kind of equipment we have in the laboratories at university, the compilation of the Linux kernel is going to take up the entire slot. Like if I have 2 hours, if I'm delivering a lab on schedulers, this is much more easier to interest people to get their hands dirty, run things. And then I would say one would be motivated to go back and look at fair.c. And then maybe in their own time, if they are motivated enough, they might come to work on the real thing. But just for the experimentation, I think this is going to be very useful for people running the laboratories and delivering operating system courses. Thanks.
Yes, I wanted to echo John's sentiment and of correctness. And I think what the skex project is not proposing, and I believe it should, is a sort of certification, validate or test that once you implement your stupid little scheduler, then I say, can you pass my test? And because a lot of the concern now is we're gonna have people writing their own scheduler. Okay, it's their own problem. It's not my code. But when I need to support them because they open me a bug, first 3 weeks is to figure out if it's their bug or my bug. They're gonna say it's me. I'm gonna say it's them. So and in the end, it turns out that they wrote a very, very crappy scheduler. Had no idea what they were doing. If there was a I don't know, a set of tests that you say, can you pass my sort of specification tests for the scheduler? And then maybe you can make them very restrictive, very, very hard to pass. I don't know.
No, yeah, Giovanni is saying about like if distro start to ship skex. Yeah. Questions. Yeah, I'm done. I'm just open to questions. Let me skip to, well, conclusion. I already said that.
Yeah, I was just going to say, so as far as I'm aware, skex, they have the interface for DVFS, but it's all still run on the
I don't see, oh, you have the mic.
On the maximum OPP. And I know, we know these comparisons are kind of bogus, but I mean, you can't really compare that to the scheduler performance that is actually in the kernel. And yeah, that kind of worries me that you throw, or that someone can throw out numbers. The performance like 15% better, while, for example, the energy or the power might be completely terrible.
Yes, sorry, I didn't get. You were saying throwing some numbers without.
Yeah, I mean, you could.
It's like it's not a good comparison.
It should come at least with like a disclaimer. Hey, here's the fair baseline, and not just here's the Linux baseline, which might use like half of the power, while only being like 10% worse or something like that. I don't know if that makes sense.
Yeah, but like the thing is like, so all these tests or these measurements are more like oh yeah, okay, I have this very specific workload and I want to optimize this very specific workload. So I grab just one measure that could be the FPS for video games. And then you see how it goes. And because the thing is, like, we're not trying to make a general purpose scheduler. We may have multiple special purpose schedulers, for example. So measuring like performance and also power consumption, yeah, it's useful, but you may also have like a specific scheduler that optimizes just a single workload. And in that case, I think it's reasonable to say, just measure the FPS of a video game and compare with the default scheduler or another scheduler. Or maybe I didn't get...
Just one last comment. No, these kind of arguments, they are good to convince people, like students, but they play against you on trying to convince Peter to make it merge. You know,
I'm not
because people are trying. Let's not. people are trying to get this merged. So but just try to represent. So if you want to try to make it something more mergeable, you should not try to
no.
kind of arguments.
This was not a talk about skex. I was just showing my user space framework. That's it.
Okay, so I think we should do like Peter and go to lunch. So we can continue to discuss over lunch. Thanks.
Yeah. Thank you.
So we will close this room. So if you want, you can let your stuff. We'll go to lunch. So so you will follow Daniel.